So I'm hoping that this clarifies this kind of natural question of what happens when you have some exponentiation happening within the logarithmic function. And we ask the question of, okay, if it's a constant for the exponent versus not being a constant for the exponent, what happens? So we're going to talk about that right now. So the first example we're going to look at is as follows. So this is technically a general claim. So we're going to assume positive real numbers, positive reals b, k, where b is not equal to 1. Then this is the following. Then log base b of n to the power of k is big O of log base b of n. That's the first thing we're going to try proving. Now, the first thing I really want you to look at is that notice that the function is defined in terms of, it's like log base b of n, right? But also notice that this is just some constant. It has nothing to do with the input over there. It's for positive reals b and k, which you could presume here are constants. They're fixed. So now the first thing we would like to do is get an idea of, okay, well, what happens here? So let's see. We'll see what properties of logarithms we can use to prove these claims. So as per usual, we should lay out the game plan for what we need to accomplish. So we find some c, which is a positive real number, right? We have to find the two constants. And n0, which is a positive integer, such that log base b of n to the power of k is less than or equal to c times log base b of n. And this has to be true for all n greater or equal to n0. So remember, that's the game plan. Usually it's quite a good idea to get cozy with this definition. So I'm just going to switch markers. So you might be staring at this and say, Dan, well, if b and k are constants, they're fixed. So what can I do? Well, think about it. We had a property we called the power law or power rule of logarithms. And it told us that we can pull this exponent here, k, out front in front of here. Now notice that if k is a constant, then there's a very straightforward way of handling this. Does everybody see it? The game plan here is we need to figure out how to make that inequality work for all n greater or equal to n0. And the natural intuition here, sorry, I'm getting very excited here. The natural intuition here is that you know k is a constant. And secondly, we know the power rule or power law of logarithms, which says we can pull this k, put it out front in front of here, so you get k times log base b of n. But if you look at that very quickly, you see that if I make c equal to k, we're done, right? I just need to use those properties. So pick c is equal to k, because I'm just going to play my lookalike game. So I'm just going to apply our lookalike approach to just make this work. But I have to do a little bit of massaging to the left-hand side to make that possible. So I'm going to pick c is equal to k. Then we find n0. We find n0 such that for all n greater or equal to n0, log base b of n to the power of k is less than or equal to k times log base b of n. Now I'm just going to use the power rule or power law, power rule of logarithms. We can say the following: that log base b of n to the power of k is equal to k times log base b of n for all n greater or equal to 1, right? So we're going to just choose n0 is equal to 1, and we're done. So therefore, now you might ask, Dan, where was the step that you got from the right-hand side? Well, notice that I'm just applying the power rule of logarithms, and it's right there. So if you find yourself wanting to advise your reader that this is the right-hand side, you can always say, which is the right-hand side, somewhere in here. Therefore, by the definition of big O, because remember, we have our two constants, we need to use the definition of big O at this stage to finish off the claim. Big O, log base b of n to the power of k is big O of log base b of n. Now, you'll notice that for some of you, you might say, Dan, why are you writing that base every time? I'll get to that in a bit. So that'll be something I'll talk about eventually. So this tells you right away that if you have a constant in the exponent like this, so when you have an exponential where this is a constant, or at least it's independent of the input, what it tells you is that this can go away. It doesn't matter. So there's a couple of ways you can imagine or think about this. Is one, through the way we talked about here in the proof. Another way you can look at this is if that's a constant, this is no different than me writing n times that, and it's some constant, right? So it really is just a finite number, but it's a fixed finite number. Where it's going to be that I'm taking n times n times n times n, doing it k times, and inside of there I can apply the product property if I wanted to, which is another way to derive the same outcome here. So notice it's a constant number though. So a very natural question is, okay, well, what happens when you change this up a little bit? So I'm going to do something a little bit spicier than just that. So let's see what happens. So in particular, actually, before I even get to that, I'm going to push this principle even further. Just because I really want to convince you that a constant like this doesn't make much of a difference in terms of big O. So I'm going to push it even further. So let's consider what happens if I take a sum of logarithmic terms, each with their own exponent, and see what happens. Now keep in mind, this is just one way to manifest this. So the claim I'm going to prove here for you is that the sum from I is equal to 1 to k of log base b of n to the power of I is big O of log base b of n. So let's play around with this. So it's going to have a very similar feel to what I did earlier. So let's see what happens when now I deal with a sum like this. So now I've raised the stakes. So now each one of these is some number that goes from 1 up to k. So it's log base b of n to the power of 1 plus log base b of n to the power of 2, and so on all the way up to log base b of n to the power of k. So now I have multiple terms I've introduced, more than that were over there. So I'm going to push this even further. So let us find constants. Remember, we always have to write out our game plan. It helps the reader. You'll notice that I'm formulating it in the way the definition would work. If I do this, then I can just invoke the definition, then we're done. And n0, which is a positive integer, so that the sum from I is equal to 1 to k of log base b of n to the power of I is less than or equal to c times log base b of n. And this has to be for all n greater or equal to n0. That's important detail. It's a very important detail. Don't miss that. So, last time we seen that we can make the constant equal to k and then we'd be done, right? But based on what you see here and how we understand what this sum is, notice that we can't just pick c is equal to k, because now we have more terms over here. But we can use the same idea, right? We can push that, we can use that power rule again, but we can push it a little further now. So notice that each one of these exponents is a 1, then a 2, then a 3, then a 4, then a 5, then it goes all the way up to k. So here's my suggestion is we pick, because I want to play lookalike the same way I did in previous lessons. So pick c is equal to 1 plus 2 plus 3 plus all the way up to k. Now if you look at this carefully, I've actually just written out an arithmetic sum. So this is just sum is equal to 1 to k of I. Now you might ask, Dan, what are we going to do with that? So what are we going to do with that? So we want to know what that means. So let's think about this. Now this is one way you can derive this if you need to offhand come up with it. Here's a geometric way you can interpret this. But I must stress that there's multiple proofs for this. By the way, this picture is not a proof. Just to be clear, you have to formalize it more. So if I have 1 plus 2 plus 3, I have 4 of them. And suppose I have this go up to k. So that means that there's k many of these columns, right? So it's k of them. Because I go 1 plus 2 plus 3. I want to know how many boxes there are here. If I know the answer to that, then I know what that sum actually equals. Well, here's another fun little trick that you can do. Well, you can take this and imagine you take this listing of boxes that I have and I mirror it. So I take this and I imagine I flip it over this diagonal here and I put the same thing that I have here on the opposing side. So for example, what I mean by this is that wherever I have the k here, I'm going to put one box here, then you would have 2 boxes here, 3 boxes, 4 boxes, 5 boxes, all the way up to the last one having k boxes. And now, if you remember back to your lessons on how to compute the area of a rectangle, well, notice this dimension is k. What's this dimension? Is that k? Or is it k plus 1? It's k plus 1. Well, what's the area of that? Well, it's k times k plus 1. But I want the half the area because the way I constructed this is I took the same number of boxes and I mirrored it over the diagonal. But I want to know what the area is. Well, it has to be exactly equal to half of this, right? Because I took it and I multiplied it by 2 by simply mirroring it like this. So this is actually how I can, this is one way I can derive this closed form geometrically, is I have k times k plus 1 divided by 2. So I compute the area of this rectangle and I divide it by 2. That's one way you can cut, if you ever find yourself forgetting about it, just draw some boxes like that. It's a piece of cake. So now this is my c. It's going to be k times k plus 1 over 2. Notice the way I formulated it, now it's in terms of k. And that is indeed still a constant because k is a constant. Don't let the fact that it looks a lot more sophisticated throw you off. It's not. Then we find n0 so that for all n greater or equal to n0, the sum, let me write it here. The sum from I is equal to 1 to k of log base b of n to the power of I is less than or equal to k times k plus 1 over 2 times log base log base b of n. Now, I'm just going to apply the power rule again, the power rule of logarithms. So notice the domain I'm using here for all n greater or equal to 1, because I want a statement that connects my selection of n0 to this next statement. For all n greater or equal to 1, observe by the power rule of, well, that's really funny. Oh, let me rewrite that. Of logarithms, we have the following. Well, what I could do is I can make use of summation properties in the following way. Notice that each one of these, I can apply the power rule to it. So I can throw that I out front, and then we'll see what happens. Well, the sum from I is equal to 1 to k of log base b of n to the power of I. Well, each one of these, I just pull the I out front inside of each summand. So I have I times log base b of n. But notice that each one of these, I'm adding log base b of n every time. But notice it has nothing to do with I. So what I'm going to do is I'm going to pull that aside from this sum in a way that makes it clear to you what's happening. So the sum from I is equal to 1 to k of I times log base b of n. But what's this? We already established that's k times k plus 1 divided by 2 times log base b of n, which equals the right-hand side. That's the right-hand side. Which equals the right-hand side. So that means that we're going to choose n0 is equal to 1, because this statement is true for all n greater or equal to 1. And then now we can just use the definition of big O and we're done. Therefore, by the definition of big O, the claim is proven. The claim is proven. And that's the end of the proof. I forgot to put the proofs. That's one thing. I need to mark the end of the proof also in our previous example, because remember, that is a proof. These are both proofs. Normally, I would write the phrase here, but I sort of ran out of space here. So just keep that in mind. But yeah, so now with these two examples, we can see that the exponent being a constant doesn't actually make much of a difference. In fact, you can take this even further, and you could say, hey, okay, well, what if I made the I k everywhere? So then you would have just k plus k plus k plus k plus k instead of 1 plus 2 plus 3. You would have just k's. There's going to be exactly k many k's, right? So that's just k squared, right? So you'd see that you could just generalize this in many different ways. Now, let's revisit this example here, seeing as it's a generalization, or you can view it as a generalization. Actually, it's not really a generalization, it's more of an extension. It's an extension of the first example. We're going to talk about now how we can apply this when I change that k to be an n, and we'll see what happens. We'll see if this technique falls apart. So before I write out what we're actually going to prove, I thought it'd be a better idea that we kind of dive right into trying to apply these techniques. And then we'll see if it actually will be, what would be the outcome. So let's do another example. I'm going to stress that this is still a claim, right? I'm just doing this for the sake of brevity. So suppose I give you the sum of I is equal to 1 up to n. Notice it's not k anymore, it's n, which isn't a constant. We're going to consider n log base b of n to the power of I, like before, except now I'm just going to replace the k with an n. We're going to try to prove that it's big O of a something. So we're going to find out what the something is. So the question is it still going to be log base b of n? So that's the real question at hand. So let's see. So the proof will have the same kind of sketch as before. So just for the sake of brevity, I'm going to omit the setup for the proof, because it is exactly the same as I had just over here. Just the exception is that you have it where instead of it being a k, it's an n right there. That's the only difference. Okay. So what I'm going to do now, you might say, okay, so Dan, what are you going to do here? Well, let's try to attempt to prove using the same technique we had before. Just before we actually get to the actual proof, because like I said, I don't want to get into those nitty-gritties quite yet. I want to convince you that the fact that that exponent is a constant actually really matters. So if I were to use the same approach over there, what would I pick as the constant? I would pick the sum, right? I would pick, so in this case, I would pick c is equal to 1 plus 2 plus 3 plus all the way up to n, right? That's what we did last time, which based on the fact it's an arithmetic series, a finite arithmetic series, this should equal n times n plus 1 over 2. And we should be able to pick n0 is equal to 1. Are there any issues with these selections of these two constants? Because remember, if I pick those two constants, is there anything I'm doing here that actually is wrong? Because this most certainly will satisfy the inequality for all n is greater or equal to n0, right? Is there any false presumption I'm making? What's the error I'm making? There's got to be something up that's a little bit weird here, because you think that if this is the case, then it should be that this is log base b of n, right? Like that should be, I should be able to accomplish that. What's the error I'm making? Because that most certainly does not make a whole lot of sense if you actually think about it, because I'm adding this. Keep in mind, one of the terms in here is log base b of n to the power of n. And if you know the power rule, it's n times log base b of n, which that does not sound like something that would be log base b of n all by itself, right? Yeah, this is the error right here. Notice that this selection of the constant is actually not a constant. This is not a constant anymore. Do you see that? Because it depends on n. So you have to be very careful when you're setting up some of these proofs to make sure that you're in fact picking a constant. So you got to make sure you clearly identify what is a constant versus what isn't a constant. K is a constant, so we can use it. Just like in previous exercises before, we talked about how we can like pick, for example, like 2 to the power of k, where k was a constant. That's a rather big number if k is rather big, but it's still a constant. But the point is that this is not a constant. That's not constant. So we cannot use this approach. It breaks apart. We need something a little bit more. In fact, if we wanted to attempt to prove this, it would be flat out wrong because it's just not true. And this is actually one way you can easily see why that mistake happens. Like I said, the last term in that sum is log base b of n to the power of n, which this is equal to n times log base b of n, which this looks more like n log n, right? It looks more like n log n. But would n log n cut it though? That's a real good question. Would n log n cut it? Well, let's look back at this. So if I were to attempt to use an approach kind of like this before, I might have to be a bit more careful though. So if I just go n log n, notice I have 1 plus 2 plus 3 plus 4 plus 5 all the way up to n minus 1 many log base b of n terms, right? But it all depends on n as well. It might be a little trickier to do it. I'll let you think about if it's true or not. Instead, we're going to prove something that would be much more in line with what we did over here. So I'm getting very excited. So notice that I have n times n plus 1 over 2, but this is just n squared plus n over 2, or 1/2 times n squared plus n, which this is quadratic, right? So if you look at this and you want to adapt this technique, you would see that this should probably be something that looks like this, right? Not just log base b of n. That's at least one thing that I'll bring up here. So the same setup for the proof with the exception. So I'm just going to, we say that we have find the constant such that for all n greater or equal to n0, this sum is less than or equal. So this is less than or equal to c times n squared log base b of n. And you might say, Dan, what should I pick for the constant then? Well, let's think about it. If you apply the power rule for logarithms, you'll end up with something that looks kind of like this times log base b of n, right? But you'll notice right away that this should remind you of something else that we're playing around with. Well, let's see, remember that's halving it. Well, what I'm going to do is I'm going to try picking c is equal to 1, and you're going to see how I might come about this. Actually, let me give you an intuition behind it. Well, you know that this is 1, 2, 3, 4, 5, 6, all the way up to n, right? Well, what if I made it so every single time it's just n here? Like there's n in there everywhere. Like instead of it just being 1, I'll put n there. Well, how many of them are there? There's n many of them. So n times n many of them, that should look like something like n squared. So that's where I'm going to go with this. I'm going to pick c is equal to 1. I'm going to try bounding it, making a good upper bound guess on what it would be. In this case, I'm going to kind of overestimate it. Instead of being I, I'm going to replace that with n. Because that most certainly will be a greater than I, given that's the highest value this sum will allow for any one summoned term. Well, one term of that sum in there for the summation. Pick c is equal to 1. Then we identify n0. N0. So that the sum from I is equal to 1 to n of log base b of n to the power of I is less than or equal to n squared log base b of n. So notice because I pick c is equal to 1. And this has to be, remember, don't forget this part, for all n greater or equal to n0. We have to have our quantifier in place. I don't want to omit any of them. So now we have this. Now what I'm going to do is I'm just going to simply apply the power rule of logarithms, and we're going to bound accordingly, okay? So we're going to apply the power rule of logarithms. Then starting on the left-hand side, so I'm going to start on the left-hand side, I'm going to derive the right-hand side, okay? That's what the strategy I'm going to use to show you that this is true for some values of n. So then starting on the left-hand side of this inequality, we have the sum from I is equal to 1 to n of log base b of n to the power of I. Well, this is equal to, like we had before, I'm just going to pull that exponent out front inside of the summand. So I have I times log base b of n. Well, this has to be less than or equal, I'm just going to overestimate now. So I'm going to have I is equal to 1 to n of n times log base b of n, right? But how many of them are there? There's n of them. So it's n times n log base b of n, which is just n squared log base b of n. And this is for all n greater or equal to 1, right? So what should I pick for n0 then? So notice that's the right-hand side. Well, I should pick n0 is equal to 1. Choose n0 is equal to 1. Thus, by the definition of big O, the sum from I is equal to 1 to n of log base b of n to the power of I is in fact big O of n squared log base b of n. And we're done. So just the main thing I really want you to take away is the behavior of exponentiation inside of a logarithm. Notice that in this case, we pushed it even further with having a sum like this. So just keep in mind that when it's a constant inside of here, it usually reduces back down to log. Those usually get eliminated. However, if it's involving n, the input of the function, that may not be the case, as we've seen in our examples.